All right, well, hey everybody. We're starting a new unit today on waves, as you can see, and a lot of this is going to build from some of the things we talked about in Physics 1250 regarding oscillations. And so some of this may be familiar. Others of it, we're going to sort of take the stuff in Physics 1250 and take it to another level. But I think this is one of the most interesting units to teach, and I hope that you enjoy it too. A lot of my research involves constructive and destructive interference, which is what we're going to talk about later this lecture. So I think this is a fascinating topic, and yeah, I'm looking forward to it. All right, so we are going to talk a lot about sound waves today. Homework 10 is mostly about sound waves. I did a little unusual thing with the homework, and I have more than one of them due on the same day, so you probably want to get working on homework 10 relatively soon, and you may not be able to do all the questions on homework 10 because I'll talk about some of that in later lectures, but certainly there's some of the questions you'll be able to do after today. Talk about the Doppler effect, talk about the power transmitted by waves, and then decibels, also a little bit into, again, constructive and destructive interference. So there's a lot we're going to talk about today. So this is the equation for wave speed, and if it was a high school course, that would be good enough, but I want to show you where this equation comes from. But the idea is that you've got the frequency of some wave, how many cycles per second that it's oscillating, you've got the wavelength of it, lambda is this symbol, and those two things multiplied together gives you the speed of the wave, and that could be a sound wave, it could be a light wave, it could be anything. Could be a gravity wave. I mean, there's a lot of different things. Where does this come from? So the best way I like to explain it is that if you have kind of a string here that you are oscillating back and forth. So this is one of the active figures from the book, and that I like very much. So you have a string, and if I start oscillating this string, the signal will kind of propagate. So it's going to start over here, wiggle, 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 and then those wiggles will sort of move this way. And so the speed of the wave is, the speed that this crest moves steadily this way. So I like this visualization because it shows very clearly the wave starting and moving. And now the wavelength of the wave is, something like this. Again, that's sort of peak to peak. The scale, but this is the speed that we're really talking about when we say the speed of a wave. Now the simple way to derive this is to say that, well, there's the size of the wave is the wavelength, and then the frequency, well, the frequency is 1 over the period, so the distance over time is the wavelength over period, and that gives you this, and again, 1 over the period is the frequency, and so that means the velocity of the wave is equal to lambda times the frequency, which is what I just had on the previous slide, right? This. So that makes some good sense, right? There's another way that I want to explain it just to kind of connect the dots between this way of thinking about waves, because this is going to come up in the homeworks, it's going to come up all over the place. So this is kind of our prototype for what a wave looks like. You have some, in that visualization I gave, you had the x dependence, right? So depending on where you are in x, that determines, how big or how small the wave is, but it also depends on the time. So at a particular time, this thing is going back and forth. So this is the kind of functional form that we're thinking about, right? So there's some kind of omega t. And so if And you can rewrite this in this way, right? Because omega, the angular speed, this is the number of radians per second. Well, there are 2 pi radians in one cycle, and so 2 pi times the frequency is the angular speed. So you'll see it written this way as well. And this way is often a very helpful way of thinking about it. So that if you have some sort of wave like this that's moving to the right at some speed, the way to think about this is sort of at what point does this thing in here maximize this wave. So for example, if I was going to follow this crest here as it moves, this crest, the maximum of the sine function, do you guys remember what the maximum of the sine function is? So it's not this. This would be, I think, sine of 270. Sine of 360 is 0, right? Sine of 0 is 0. Sine of 180 is 0. But sine of 90, that's 1. And so whenever this is equal to 90, or whatever the radian's equivalent of 90 is, pi over 2, whenever this is equal to 90, that's when the crest is. And so if we think about how quickly that crest moves, that can tell us the speed of the wave. And so if I say, all right, well, our crest, this position, this is going to be the position of our crest, is going to be like this. So let's say that little n is equal to 0. That gives us pi over 2, so that's 90 degrees, right? So if this is equal to 90, this whole thing is equal to 90, then we're on the crest. But that crest is moving because time is marching on, my friends. Time is marching on. There's no way around it, I'm afraid. And so here's the time. And so what we need to do is we need to figure out how quickly does this crest move forward. So what we want to do is we want to solve for this crest. Again, this is for n equals 0. I could do n equals 1. That would give us 1 plus a half is 3 halves, which takes us to this peak. So we could do that one too if we wanted to. But let's just keep n equals 0. So again, I'm going to solve for the crest here. So I'll multiply both sides by lambda, divide by 2 pi. I should change that to 0, 1, 2, 3. And so again, if I solve for the crest, again, I'm going to multiply both sides by lambda, divide by 2 pi. I'm going to add this thing to both sides, right, because I want it to be over on this side. Multiply by lambda, divide by 2 pi, I get the position of the crest. So I get some cancellations here. At the end of the day, I end up getting the position of the crest is equal to the frequency times lambda times the time. Does that look familiar? The position equals something something times the time. Well, that's the velocity times the time, right? And so just from this formula, you can infer that the velocity of these peaks, whether it's n equals 0, 1, 2, 3, the velocity of these peaks march forward at f times lambda times the time. In other words, the velocity times the time. So that's kind of a more mathematically sophisticated way of saying it, but it still kind of makes sense. So there's a nice video that I'm going to show in a second. If you want to pause this and watch the video on the embedded PDF, you can. So I only recently realized that my PDFs actually have the videos embedded in them, so you just go and you click and it works just fine. And so you might want to watch it there and then come back to this. That's fine. I'm going to go ahead and play it now. And hopefully that will, the sound will be okay. The sound might be slightly better from the PDF, I'm not totally sure. But anyway, here we go, Doppler effect.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out.
Oops, there you go. So I hope you enjoyed that video. One fun thing about that video is that the episode of Big Bang Theory that Sheldon Cooper quote comes from, Sheldon is dressed up as the Doppler effect for his Halloween costume. But I thought his definition was pretty accurate. This is a figure talking more about the Doppler effect. We're going to try to make this a little bit more mathematical. And so this is an ambulance that's emitting a signal because its sirens are on, and there's a little person here that's kind of listening to it. I don't know why an ambulance would be sitting with its siren on, not driving in a particular direction, but if it was, this is what would happen. And these little circles, they represent sort of the peak of the wave, right? We talk about the sine wave and there's the crest. These little circles are the crest, and so because we're talking about sound waves are fluctuations in the density of the air, and so kind of the max density is sort of along this circle and along this circle. In principle, in the middle here, that's where the lowest density is. And so this is kind of what that's visualizing. But again, if the ambulance is kind of just sitting there, its sirens are turned on, there's some wavelength of the sound. Sound is going to move at the speed of sound, and so it's going to move, this way and that way and up and down. It's going to look like that. Now, but if the ambulance is moving, well then what happens is that the ambulance is kind of closer to our observer at B for the next time that the crest is produced by the speakers that are on the ambulance. And so the effect of that is to make the wavelength shrink. So let's talk about that for a minute. So this is when the ambulance is at rest. So again, this is the position of one of the crests and the position of another crest. And so the difference between those two things just depend on sort of the difference between those two things just depend on, how fast is the speed of sound and how long ago was the thing emitted, right? So there's a speaker on this thing that's emitting a signal. And so crest 1 is moving ahead at its velocity times the time. Its velocity is the speed of sound times the time. And then crest number 2 is speeding ahead at the speed of sound times the time, but it's delayed. So the second crest doesn't happen until one period later. And so as a result, this second crest has not moved as far. What we do know is that the difference between these two things is the wavelength, and so that's exactly what we have here. So the wavelength here is the difference, and what's interesting is that even though this crest is marching forward and this crest is marching forward, the separation between the two is always constant, so the time dependence here cancels out. So speed of sound times the time here cancels with this speed of sound times the time. You end up with just the speed of sound times the period. And so the wavelength here is related to the speed of sound and the period of the wave. which maybe isn't so surprising, right? Because we learned before that the frequency times omega equals the speed that the wave is moving, right? And so that's certainly true here. But I just wanted to sort of spell this out so that a second from now, when we let the ambulance move forward, we can kind of incorporate that. Okay, so we're going to let the, so we already knew all that. We're going to let the ambulance move forward, and now the wavelength is a little smaller, and crest number 1, let's say, was emitted here. Crest number 2 was emitted a little bit later. So we're going to call this lambda prime. This is not because I'm talking about a derivative. I don't know why the people in the math department like doing the prime things as derivative. Prime in physics often just means like the new wavelength, the different wavelength. It's, again, not a derivative by any means. Excuse me. So this first crest, because it's emitted here, is exactly the same as it was in the previous example, right? It's emitted there, and it moves forward at the speed of sound. So you're going to see a factor of the speed of sound times the time here, right? That's exactly the same as we had before. The second crest is where things get interesting because it's emitted later, right? But over the time, over that period of the wave, the ambulance has now moved some distance closer to us. And so this crest number 2 is closer to our little observer than it would otherwise be if the ambulance was at rest. And so we can just put that in as the velocity times the time. What's the time that matters here? Well, it's the time between crests of the waves, is how far this ambulance has moved. And so as a result, these two things are a little closer to each other than they were before. And they're moving forward. They're both moving at the speed of sound. The thing I want to emphasize here is that it's not as if the second crest has a different velocity. It's not as if this thing is moving at the speed of sound and this thing is moving at the speed of sound plus the velocity of the ambulance. That does not make any sense because it implies that like eventually crest 2, because it's moving faster, like gets ahead of crest 1, which doesn't make any sense. It's not at all what happens in real life. In real life, you always get this signal first, then this signal. So again, this is the position of crest 1. This is the position of crest 2. Again, there's this extra little bit because the ambulance is moving. And they're both marching forward in time, right? Because little t is increasing as time goes on. But this factor of t cancels with this factor of t, so that this wavelength is always the same. Crest number 1 is always a little bit ahead of crest number 2. They're both moving at the speed of sound. It's just the one is slightly delayed from the other. And so at the end of the day, the little t cancels, and you get the speed of sound times the period minus the velocity times time, right? Because there's a minus sign here, and so if the ambulance has moved this much, that's going to make them a little bit closer together, and so the wavelength is going to be a little bit smaller than it was when the ambulance was stationary. So that's what we get. And so from here, we can kind of rewrite this equation in a couple different ways. One way we can rewrite it is by noticing that this factor here, c sound times the period, is actually the original wavelength. So that's one way to write it. We can also write it in terms of, we can also divide by the original wavelength and sort of write it this way. So dividing by c sound times the time, end up with something like this. So again, the ratio of the new wavelength to the old wavelength is this. And the v here assumes that the velocity is positive, and basically it's assuming that a positive velocity is an ambulance that's moving towards you, is what this means. And so because this is overall slightly positive, 1 minus slightly positive thing is going to be less than 1, and so our wavelength is going to be a little bit smaller because the ambulance is moving towards us. So this is what I derived. You can also multiply both sides by lambda to get something like this. And the idea here is that the wavelength that is emitted here is multiplied by this factor to become the wavelength that you actually observe with your ears or the microphone or whatever else you got. Um, and so I emphasize here that I've been using speed of sound the last few slides, but really this applies for any kind of wave. And so for electromagnetic waves, they're going to be moving at the speed of light. Gravity waves will be moving at the speed of light. So I just, any kind of a wave that you've got, whatever the speed of that wave is what the velocity is divided by. Bear in mind, if the ambulance is moving the opposite direction, the velocity would be negative, and so that would make the observed wavelength a little bit longer. And so if the ambulance is going away from you, you would detect the wavelength to be a little bit longer. And so this equation actually supports that. The next thing we want to do is say, all right, well, if this is what the wavelength is doing, what is the frequency doing? So we can sort of take this equation and do the same kind of thing. How much time has passed, right? Because the frequency is related to how many cycles per second. It's related to the period. And so both these crests are traveling at the speed of sound, and so the time difference between those things, even when the ambulance is moving, if you follow the same kind of analysis that we did before, again, this is the new wavelength divided by the speed of sound. Well, we know what the new wavelength is. And so you can say, all right, well, if this is the new period, then the new period is 1 over the new frequency. So kind of like that, you can invert that, 1 over that, and get something like this. One way or another, you kind of end up with this. It's not too hard to go from this thing to that. I hope you would agree. So what's interesting is that this is the emitted frequency. And again, if the ambulance is moving towards you, V is positive. And so you have 1 minus a slightly positive thing, that's going to make this less than 1. Dividing by something that's less than 1 is going to make this thing more than 1, and so the observed frequency is going to be more than the emitted frequency, which is why that pitch goes up instead of down when you hear the car coming towards you. And then the opposite happens when the car is moving away, is that the velocity here is negative, and you divide by something that's slightly more than 1, and so that's going to make the frequency drop. My brother actually he teaches marching band, and so he and I had an interesting conversation the other day about, when you're marching, you're moving, right? And so how does that change the pitch of the instruments? And is it a big enough effect to actually worry about? Or not? It's a good question. This is a real bumper sticker from the American Physical Society, and I think it's kind of clever here, and it says, if this sticker is blue, you're driving too fast. And so the joke here is that if you're driving quickly, then this red light is going to Doppler shift into the blue. And so if you make some assumptions here to say, all right, well, let's say that this light is something like 700 nanometers or so, and if blue light is something like 450 nanometers, you put 700 nanometers here, 450 nanometers here, try to solve for what this velocity has to be. And given that we're dealing with light, the speed of light is 3 times 10 to the 8 meters per second. Then you can solve for this in terms of miles per hour, and you end up needing to go a significant fraction of the speed of light for this thing to get Doppler shifted from red to blue. And so this is part of the joke, is if you're definitely driving too fast if you're going a fraction of the speed of light. So there you go. You guys are in on the joke now. You can enjoy it with the rest of us nerds. All right, the next thing to talk about is what's called wave superposition, which is related to this constructive and destructive interference, as we'll talk about. The next video talks about how this principle is behind noise-canceling headphones. I myself do not have a pair of noise-canceling headphones. Maybe you do, but I hear that they work reasonably well. And so this is sort of how they work. And I have to mute my microphone real quick before we do this. You guys can also watch this on the PDF video. The sound might be better.
See the universe through a brand new set of eyes.
Hello, my name is Jack Conti. I am here in Wonderfest Studios to spread some physics love. We're going to talk about waves. Waves are freaky, and wave behavior is a big part of what makes quantum physics so weird. Wave behavior also explains sonic booms, rogue ocean waves, and all kinds of strange phenomena, including noise-canceling headphones. Noise cancellation works because of the key wave phenomenon, interference. Let's start with the interference of two waves, because we've got to understand two-wave interference if we're going to understand noise cancellation. Let's choose waves that we can see, like these waves in a super long metal slinky. As the wave moves through the slinky, notice that the loops of metal just move back and forth. The slinky itself isn't actually going anywhere. The wave moves, but the slinky hardly moves at all. So we see that a wave isn't really a thing. It doesn't have mass. A wave is a disturbance in a set of things that have mass. Here, those things are metal slinky loops that can pull and push each other. In sound waves, those things are air molecules that can bump into each other. So, sound is a systematic disturbance in air molecules. The disturbance starts at a vibrating source, say a jet engine, and travels as a wave all the way to your ear. As the air molecules in your ear vibrate back and forth, they make your eardrum vibrate, and then you hear. Suppose that the note you hear is middle C from a synthesizer. This means that the air molecules inside your ear that are vibrating your eardrum are moving back and forth at a rate of 256 times per second. 256 vibrations per second is the frequency of middle C. But suppose you put a headphone speaker next to your ear, that is what headphones are, by the way, tiny speakers, and the headphone speaker also makes the air vibrate at 256 times per second. Then the two sound waves might add. The back and forth motion of the air molecules in your ear, caused by the synthesizer, might add to the back and forth motion of the air molecules in your ear, caused by the headphone speaker, and the sound would seem extra loud. This is an example of constructive interference. But what if the headphone made the air molecules not vibrate back and forth, but forth and back? Then every wave that came from the synthesizer would make the air molecules vibrate back and forth, while every wave that came from the headphones would make the air molecules vibrate forth and back. The waves would be perfectly out of sync. The pushes would cancel each other out, and the air wouldn't vibrate at all. There would be no sound. This is an example of destructive interference. That's exactly what noise-canceling headphones do. They produce sound that's out of sync with the other sound that's hitting your ear. Every noise-canceling headphone has a tiny microphone that reads the incoming back and forth sound wave frequencies. Internal electronics then make the headphone speaker produce forth and back sound wave frequencies. As these two opposing vibrations combine in the air near your eardrum, you hear nothing. Well, nothing is what you would hear if the headphones worked perfectly, but incoming sound waves are rarely pure tones. Jet engines produce a ton of different frequencies of sound, so your headphones have a tough time producing all the same frequencies but flipped out of sync. It's sound wave destructive interference, and it's the physics that's making Dr. Bose and Dr. Dre rich.
Check. Alright, I hope you enjoyed the video about noise cancelling headphones, things like that. The next thing to talk about is the power in sound waves. So if you are an electric guitar player, this is something that you care about very much, because when you go to buy an amplifier, you want to know how many watts of power does that amplifier produce, because that helps to figure out how loud it would be in a particular concert or whatever. So this is the formula for that, and this is the angular speed radians per second for the sound waves. Because we're talking about sound, we're probably going to switch this to just frequency pretty quick. And then there's various other terms here that I'll explain. So one of the terms here is the density of the air, and that one is there because I don't know if you guys have ever heard this: in space, no one can hear you scream. And so the idea there is that sound waves have to propagate through something. They have to have some medium to propagate through, and so usually it's the air. But in principle, you can also have sound go through the water. So there's sonar, things like that. But in space, you have pretty close to zero density, and so if you are an astronaut and your radio breaks and you scream inside of your spacesuit, no one can hear you scream because there is no medium for that sound to go from one place to another. So the power that you're able to transmit is not so much. So that's one of the terms here. Another term is sort of the area that you're moving through. And so the larger that area is, perhaps the more power of waves that you would, that we're talking about. Especially if you're like at a concert and there's some speaker over here and you're trying to figure out how much power of sound waves get over here. Well, if you think about the sound waves going through this circle compared to the sound waves going through this circle, that's going to be more through this circle, right? Because it's a bigger circle. And so it makes sense that the area is there. And then this is the max displacement of an air molecule due to the sound wave. And so the sound waves are variations in the density of the air. And so to have that variation density, you have to have actual air molecules being in a slightly different place than they would otherwise. And so that's why this is important. And of course, the louder the sound wave, then the more that movement is, the more that displacement is. And so that's why this kind of makes sense to be there. So that's the power of the sound waves. You probably don't remember the formula for the power of waves on a string. I myself probably didn't really remember it very well, but this is the formula for the power of waves on a string. And so you see a lot of similar terms. You see it depends on the frequency here, angular speed, whatever. You see that, whereas here you have this sort of change in position to the molecules squared. Here you have the amplitude squared, right? Because you have some string that's going up and down, and it might be going up and down a lot, or it might just be going up and down a little bit. And then you have the density of the air here, whereas here this mu factor is the mass per unit length of the string. So maybe you have a nice thick string, that would be a large number. If you have a lightweight string, fishing line or something, that might be very small. There's a wide variety of things here with these two equations that have in common. And basically this whole displacement thing with the molecules, I think it's safe to call that an amplitude. And so the important thing is that the power of a sound wave has to do with the amplitude squared, and that's going to be very important in just a minute. All right. That's right. The power is the amplitude squared. And so there's various ramifications for this for sound waves, various ramifications for this for electromagnetic waves. But yeah, so this is one of the, again, I don't expect you to memorize all this, but you definitely need to understand that that this is true. Okay. Now, what we often do here is talking about the power of a wave. Again, this just goes back to this formula. Well, the larger the area, the more the power. Well, what if we weren't interested in the power? You just want to know what the intensity is. The intensity is the watts per unit area. So for example, if I'm at a concert and I might be interested in how much power and sound waves is going through this circle and how much power and sound waves is going through this circle, but instead of having my results depend on how big of a circle I'm talking about, I might just want to know what the intensity of the waves is, because the intensity of these sound waves going through this is going to be the same as the intensity of sound waves going through that, right? So I might just want to divide the power by the area that we're talking about, and then I end up with this function. And so this is typically how we measure sound. We typically do not measure sound in terms of power, we measure it in terms of intensity. However, it is true that when you go to buy a guitar amplifier, they measure it in terms of the power. it would not make sense to measure the guitar amplifiers in terms of intensity, because if you're really close to it, then it's really super intense. If you're far away, it's going to be less intense, as we'll talk about in just a minute. If you think about the total intensity, right? Because this area, if you imagine this area is the entire sphere around, say, your power amplifier, well, that sphere has an area of 4 pi r squared. So again, when you buy a guitar amplifier, it's the power that they give you, and that allows you to, if you wanted to calculate how loud it would be at different distances, you could do that. All right. Also happens to be true for electromagnetic waves. So there's another video here. So I'm going to turn down my volume and let you guys look at that. This one has to do with constructive and destructive interference. It also has to do with power, and a little bit to do with this. So that's what's coming. So let me turn my mic down.
Hey everybody, thanks for checking out D-News today. I'm Trace. Now listen up. Sound is extremely powerful. It's made of invisible waves of energy passing through substances, ground, water, air, particle to particle. The human ear can perceive these waves as long as their frequency is between 20 hertz and 20,000 hertz. Anything above or below that we can't hear, but they're still there, because these waves contain energy. And with enough din, you can make these waves do some incredible things. Outside of medical technology like ultrasound, one of the most commonly known ways to make sound do something is by breaking a glass. This works only when the sound wave is at the exact same frequency as the object you're shooting at. If you gently flick a wine glass with your fingernail, you will hear its frequency. Match that tone and turn the volume up, way up to like 11. And that glass will probably break. Also within the range of hearing is sound levitation. This is way cooler than breaking stuff, if you ask me. Sound levitation has been around for years, but until recently, we couldn't do much with the stuff once it was levitated. It just sort of hung there in the air. Thanks to advances at a Swiss university called ETH Zurich, we can not only levitate stuff, but we can move it around, adjusting floating fluids. This works by using the energy in the sound waves. In this apparatus, the energy waves reflect back and forth so quickly they form what's called a standing wave, or a specific point where the energy from the sound can hold an object in midair. Think of it like these silly executive desk toys. The ball in the middle, that's the standing wave. The thing that they just figured out is how to move the stuff once it's levitating. Now they can use this system to manipulate liquids, combining and separating them, all without touching them with human hands, which is immediately applicable to drug manufacturing. That's kind of cool. These energy waves can do a lot of other stuff too. The LRAD, or long-range acoustical device, is a weapon that shoots sound. It's like a sonic death ray, but without the death part. It can produce so much sound that you feel physical pain, like 160 decibels. That's loud. Think NASA rocket launch. But it won't kill you. It just really hurt, like a sonic hurt.
All right, so there's a question on the homework that has 2 speakers, and you need to calculate, say, the frequency so that those 2 sound waves cancel each other out at a particular position. So that's actually a pretty tricky problem, and I want to give you guys some kind of tools to approach that problem. And so in the next slide, we're going to talk about that situation where instead of destructive interference like it is on the homework, instead we're going to do constructive interference. And basically it's going to be a weapon, is what it is. And so the basic setup of the worksheet, there's 2 worksheets for this lecture that I'd like you to do. The first one is on power lines, but the second one relates to this situation. So let's say that my friends at the Air Force Research Lab are being attacked by this guy who may or may not be from the Tiger King Netflix series. So what we want to know is what is the lowest frequency to get the maximum sound in this case. So the idea here is that we have 2 speakers, but if we can get those waves to overlap in exactly the right way, then we can have twice the amplitude of each individual speaker here. And that's important because if you have twice the amplitude, remember that the power goes as the amplitude squared. And so if you can set this up in exactly the right way, using exactly the right frequency, you can potentially have 4 times the intensity of sound here than you would if you just had one speaker. And so in a certain sense, it's kind of like a 4 for the price of 1 sale, right? You could buy 4 speakers and set it up that way to try to deafen people. But maybe the military can only afford 2 speakers and you just need to do the best that you can, right? And so the worksheet is going to kind of walk you through that problem. I should say the premise of the worksheet, you might wonder, why are we trying to find the lowest possible frequency rather than the highest possible frequency, or a frequency? And the answer to that is that it's very hard to make ridiculously loud, very high frequency sound, so ultrasound basically. For one, it's hard to make that super, super high intensity sound, right? For two, think about the wavelength of those waves at very, very high frequencies. Well, the wavelength gets smaller and smaller. And so that means that if you manage to get constructive interference here, this person might be able to move just half a wavelength and be able to move to a place of destructive interference, in which case all of your efforts are basically for nothing. And so for high frequency sound, that wave, that distance might be this much. So you turn on the speakers and they just move their head by this much and now they're fine, right? But for lower frequency sound waves, the wavelength might be this big or this big. And so you can do, so for example, if you had a particularly low note, might be 100 hertz or something like that. Like if you play bass guitar, like 100 hertz is close to some of the notes there. So the speed of sound is 343 meters per second. Speed of sound divided by the frequency, so 343 divided by 100. Well, for 100 hertz, that's 3 meters of wavelength. And so if you can make that frequency, then they're going to have to move 1.5 meters to get away from where that constructive interference is. Or something like that. So again, that's why we want to find the lowest possible frequency there. So I hope you enjoy that worksheet. It's an interesting one, and again, it helps very much on the homework. Now, in terms of the way that we measure the intensity, in the video they talked about how I think it was 160 decibels is loud enough to cause significant pain. So this is how we measure that. We take the intensity of sound. Intensity is measured in watts per meter squared. Often this intensity is in 10 to the minus something or other watts per meter squared, because your ears are very sensitive. And so we can divide it by that. Then we take the logarithm, and for whatever reason we multiply this thing by 10 again. And so that basically means that quiet sounds are like 60 decibels, but really loud sounds are 120 decibels. As you know, my ability to enunciate is down in the 20 decibel range, but this is the formula you use. I believe there is a question on the homework that asks how you would do that. So that was an example with sound waves interfering. There's a fun example with electromagnetic waves interfering, which is in this video here. And I found this a couple years ago. I thought it was pretty interesting. And so this is a simulation of a Wi-Fi access point. And I don't know if you've ever noticed this, is that different rooms of your house have different Wi-Fi signals. So for example, in this house, this room here has like an okay Wi-Fi signal. This one has an okay Wi-Fi signal. Maybe this one not so much. Maybe this room not so much. And it's a little bit hard to guess as to exactly exactly where in the house you're going to have good Wi-Fi strength. And then if you're standing here in this dark patch, then for no especially good reason, all of a sudden your internet signal drops significantly. And what's interesting is that these lines relate to the wavelength of the waves that you're using. So if you're using 2.4 gigahertz Wi-Fi, which most people are, the speed of light divided by 2.4 gigahertz is, gosh, I forget how big that is. I think it's, something like this. And so you can see that scale imprinted on these kinds of maps. Now, what would really be interesting if you could literally walk around your house and find this kind of interference. In a certain sense, you can kind of see the wavelength from this video, right? Because you can see the crest to crest distance. And basically, this distance is not so different from the space between these lines and stuff like that. What would be really fun is if you could walk around your house and just download an app on your phone or your iPad and say, all right, well, in this room, I can tell that it goes up and down, and I can detect this pattern in my house. That would be really cool. Unfortunately, these these lines of destructive interference and things are hard enough to find that the apps that you can download to measure the Wi-Fi strength in your house, those apps don't have enough fine-grained ability to see that. So they can tell you overall in this room what the Wi-Fi signal is, but they're not going to be able to pick out features like this or like that. So you can still play around with it. You can download it and see what you see. But Wi-Fi signals are one of the frustrating ways that wave interference matters in our everyday life. I'll show you guys this video again. It's kind of fun. So as it propagates, you get these reflections, and then certain things cancel out because you can get reflections off of walls, but then it also sort of goes through walls. Things like that. Now this is another example, and so this is an interesting situation where you put a bunch of marshmallows in the microwave. The microwave has intense electromagnetic waves in it that are at microwave wavelengths. Microwave wavelengths are a few centimeters. Most microwaves operate at about 2.4 gigahertz-ish, surprisingly close to where the Wi-Fi signal is. So if you've ever noticed that when you're making popcorn in the microwave that all of a sudden Netflix stops having efficient downloading, then that's what happens. But what's interesting is that we can play this back again, is that when you run the microwave, and you're trying to melt all this stuff, it does not melt evenly. And you notice that there's certain spots in this thing that are more melted and more burnt than others. So that's a spot that's especially melted, but over here it's fine. Here's another spot that's very melted, but then next to it it's all fine. Here's another spot that's extra melted, but then next to it not so much. And so what's happening is that you have electromagnetic waves in your microwave that are traveling past each other. And there's certain spots in which they constructively interfere and things get really melted. And then there's other spots where they destructively interfere, and these marshmallows might not have gotten very heated up at all. And it all relates back to constructive and destructive interference. In fact, the whole reason why you have that plate that rotates in the microwave is because they know about this. And if your food didn't rotate, then it's likely that part of your food would be in one of these cold spots and another part of your food would be in a hot spot, and you get very uneven heating of your food. And so that's why that plate spins around. So that ultimately comes down to constructive and destructive interference. So that's about all I had for today, but I want to talk about the worksheet real quick. So there's actually two worksheets. There's a worksheet on power lines, and then there's a worksheet on speakers. So let me bring that up real quick. The power lines one is first. And I know you're wondering why in the world are we talking about power lines now? Well, if you look at pretty much any power line, I'm looking out my window now, see if I can see any, but if you look at any power line, you often see there's 3 wires here. And what's interesting is that all 3 wires are carrying current. So it's not as if one of these is ground. And this is what's called 3-phase power. And so if you measured the voltage of these 3 different wires, you would get these 3 different curves. So let's take the black curve, kind of does this. Again, if I take a voltmeter on this thing and measure it with time, the voltage goes positive, it goes negative, then it goes back to 0. So we have this sine wave. Wire 2, that voltage starts negative, it goes more negative, comes back up, crosses 0, peaks, comes back down again, and does something that's similar to the black line but different. And then the blue line starts positive, goes negative, goes back up and goes positive. And no two of these wires are doing exactly the same thing. Now, the nice part about this, the reason that from an engineering perspective that this is a fairly smart thing to do, is that if you only had one wire, and if that wire was carrying AC current, then the power in your device, if you're running a motor, powering a resistor, powering something, the power in that device is related to the voltage that the power lines are supplying. And so if all you had was wire 1, then here you've got nice 50 kilovolts of power. Here you've got negative 50 kilovolts of power here. That's great. But right in the middle you've got 0 volts of power. And so over this cycle, and as you probably know, this cycle happens at 60 hertz, right? 60 times a second. It goes back and forth like this. So that means that, let's see, so this is 1/60th of a second. That means every 1/120th of a second, no, I'm sorry, every 1/30th of a second, right? Because you have a 0 crossing here and a 0 crossing here. Every 1/30th of a second, your voltage goes to 0 and you get no power. And so if you're trying to start an engine up, so let's say you're trying to start an electric motor and trying to get it going as fast as you can, starting from rest, well, it's not going to help you that this wire has 0 power every 1/30th of a second. But if you have 2 of these wires, then when one of these is 0, the other one is non-zero. And 3 wires is even better, right? Because it's even it allows you to have moments where at least one of the wires is doing something useful. So this actually works out to be kind of a smart thing to do. In more detail, it's really about if you're actually using this in an engineering context, you're really using sort of the differences between the wires. So, for example, at this moment, you might want to use this wire compared to like the blue line or the black line. That gives you a voltage difference that's even more than this 50 kilovolts. So this is 50 kilovolts compared to 0, but you can get an even bigger voltage difference from going from here all the way down to here. And so if you read about three-phase power, you'll hear there's this extra factor of 1.73 that often comes in. So for example, so for 120 volts, if we were in the classroom, I could point to you at the fuse box and I'd say, you see how it says 208 volts there? That's because it's 120 times 1.73, and it has to do with the difference between here to here and here all the way down to here. So this is a larger voltage difference, and it's the voltage difference between 2 wires instead of just 1 wire in the ground. Anyway, that's a long story. So this is a smart thing to do, and you'll see how when you subtract these 2 wires together that where this factor comes from, 1.73. And so what I want you to do is to try to fill this out and say, okay, well, there's some amplitude here, there's some omega, and then there's some phase shift. Now, one of the trickier parts of this question, this worksheet, is trying to figure out what these phase shifts are. At least it was the last 6 years I've been doing it. But I've given you a hint on the phase shifts. And so I've added these dots here. So for example, this first wire number 1, there's no phase shift on wire number 1 because when t equals 0, the sine function is 0, and so you get 0 here. But for this wire number 2, I've given you this little hint here, which is that at this point, wire number 2 has a voltage of 0 relative to ground, which means, but the time is non-zero. The time is not 0 here, and so this thing minus this thing minus the face had better add up to 0 because that's what it is there. Okay? And so that can help you figure out what in the world this phase shift has to be. And then same thing with this wire is that at some later time, this sine function is equal to 0, and the time is non-zero, so it can't be because of that. Instead, it has to be because this thing ends up being equal to the phase. And so if you kind of stare at these, I have the angles written down there, that can try to help illuminate that. So that's the idea of this worksheet. And then once you have these equations figured out, well, you can think about subtracting this sine wave from this sine wave and trying to figure out what the largest voltage is across those two things. And this is a nice trigonometric identity. This is basically my favorite trig function, right? Because it takes two sine waves and it produces something it's a very interesting result out of them. And you're basically going to try to use this thing to figure out what that factor is. And actually, the second worksheet, the one that's on the speakers, that's also going to take advantage of this formula. So that's kind of an introduction to the worksheet. So you can go ahead and start on that. Yeah, send me an email if you have any questions.